Welcome to this video lecture on pushdown automatas. In this, I will show you how PDAs work and I will solve a simple example to give you a better understanding. PDAs are just like NFAs and DFAs. They are used to check whether a given string is a part of a language or not. However, PDAs are more powerful because they consist of a additional component which is the stack. Let us look at it in detail. This is how we can visualize a PDA. A PDA consists of three main components. Let us look at each component one by one. So the first component is the input tape. The input tape has a series of input alphabets or characters. So over here the characters are 1, 0, 1, 1 and so on. The next component is the stack. The stack is a simple data structure on which three operations can be performed. The push operation, in which an element can be inserted at the top of the stack, a pop operation in which the topmost element of the stack gets removed, and a seek operation in which nothing happens, nothing changes, but only the topmost element is returned to the calling function. Now in PDAs there is a special characters which we will call as dollar. This signifies that we have reached the bottom of the stack. So if we do a seek operation and if a dollar is returned, it means that the stack is empty because there is nothing below the dollar sign. It is important to note that we can neither push or pop the dollar sign. The last component is the finite control. This can be thought of as the CPU of the automata because it controls the manipulation of the stack, like which element is to be popped or pushed, and reading head. The reading head is basically a pointer to the input tape and it points to a single character at any given time. The finite control reads the input tape with the help of a reading head and it reads from left to right. A stack is manipulated by the control logic with the help of three inputs: the current state of the machine, the input character of the input tape, and the current stack top. So, if the conditions are proper, then an element may be pushed or popped from the stack accordingly. Let us discuss the push operation. So over here, we have states Q1 and Q2. Q1 is known as the start state because it is being pointed by an arrow. When the machine boots up or starts, then the current state of the machine would be Q1. Q2 is the final state. We know that because it is being represented by two concentric circles. If the machine halts in state Q2, then that means that the given string is valid for a given language. In these two states, a x slash ax. A is the input symbol. It is the symbol which is encountered by the reading head on the input tape. So right now the reading head is pointing to small a. The next thing is stack top. Stack top is the topmost element on the stack. So it's saying that the input symbol is A and the stack top is capital X. The final part is AX. This is the output part. So if these three conditions are there, if the state is Q1, if the input symbol is A, and if the stack top is X, then the stack is updated to AX. So an capital A is pushed on top of the stack, which makes the new stack as AX, and then the rest of the stack. This can be mathematically written as delta of Q1, A, X gives Q2, AX, where the first part is a function which consists of the input and the second part consists of the output. The input consists of the state, the input symbol, and the stack top, and the next part consists of the new state and the updated stack. Let's have a look at the pop operation. Over here we have the start state as Q1, the final state as Q2, and A as the input symbol and X as the stack top. Now, when we have the start state as Q1, input symbol as A and stack top as X, then we replace the topmost character with epsilon. Epsilon is null character and it means that the topmost character is replaced with nothing, which pops off the X, like so. Let us define a pushdown automata formally. So a pushdown automata is a 7-tuple entity. These tuples are Q, sigma, gamma, delta, Q naught, Z naught, and F. Let's have a look at each one by one. Q is a finite set of states. So in our previous example, the states were Q1 and Q2. Sigma is a finite set of input symbols. Gamma is a finite set of stack symbols. So the difference in these two is that sigma, the input symbols are present on the input tape and the stack symbols are present on the stack. So we can push, pop or seek stack symbols and we can read input symbols. Delta is the transition function. It is divided into two parts, the input and output. The input is Q, sigma star and gamma, and the output is Q and gamma star. Notice the star at both these places, both the ends, input and output. In the input it is on sigma, which signifies that the string is empty. So if we encounter a epsilon, it means that the string is empty. Otherwise there is some input symbol. On the output side we have gamma star. Star means that we can have epsilon in the string. So if it is epsilon, it signifies a pop operation as we have just seen in the last slide. Q naught is the start state. The start state is the state in which the machine boots up in or starts in. So obviously it has to be a element of Q. Z naught is the initial stack top. Initial stack top, if we encounter Z naught, then that means that the stack is empty because it is the first element in the stack. And obviously it has to be an element of gamma, the stack symbols. F is a finite set of final states. Final states are the states in which the machine is expected to terminate if the string is valid. So if the string is valid, the machine has to be in one of the final states. And the final states obviously has to be an element of a finite set of states, which is Q. Let's discuss how to solve PDA problems with the help of 4 steps. The first step is designing the logic. In this step, we decide on the states, what each state stands for, and how the problem will be solved with the help of these states. The second step is designing the transition function. In this step, we make the transition function delta and we represent it by a state transition diagram or with the help of a table or mathematically. The third step is specifying the remaining tuples that make the PDA. The remaining 6 tuples are Q, sigma, gamma, Q naught, Z naught and F. So we write down the values of these tuples. The last step is testing the logic with the help of examples. So in this step we take strings uh, and we put it in the transition function. If in the end we get a state which is a final state, that means that our logic is correct and we've solved it correctly. Otherwise we repeat this process again. Let's look at a simple example. So the question is like, design a PDA that accepts strings of the language L where L is equal to a raised to n, b raised to n such that n is greater than 0. So the first step in solving this type of sum is designing the logic. So let's have a look at some of the strings which are possible with this language. Some strings are AB, AABB, AAABBB and so on. So with this we can conclude two things. First, there are equal number of A's and B's. This is because the exponent n is same on both A and B. Secondly, we can conclude that first all A's occur, then all B's occur. So in the above example strings, we clearly see that A's occur first and then B's occur. So the logic for solving this sum is that pushing a stack symbol on top of the stack when we encounter a A and popping out that stack symbol when we encounter a B. So in the end, we should be left with an empty stack if it follows this language. If we're left with an empty stack, that means the string belongs to this language, otherwise it doesn't. So for each A encountered, and if a pop hasn't occurred already, push an X on the stack. X is our stack symbol and a uh, pop should not occur because first all A's occur and then all B's occur for a valid string. For each B encountered, pop X if X is on top. X has to be on top because first all A's occur and then all B's occur. If X is not on top, that means our string is invalid. If the string has been passed, that is, there are no more characters remaining and at least one pop operation has occurred, then accept it. So as I said, if in the end we're left with an empty stack, then we should accept the string. And there should be at least one pop operation because n is greater than 0. So at least one pop operation has to be there. If n would have been greater than equal to 0, then the pop operation was not necessary. Let's design the transition function, which is step 2. We'll do this by drawing the state diagram. For this solution, we can have three states, Q0, Q1 and Q2. Q0 signifies that A has been encountered, Q1 signifies that B has been encountered, and Q2 signifies that string has been accepted. So when an A is encountered on the input tape, then we push an X as per our logic. So if the stack top is either dollar, that is empty stack, or if the stack top is X, then we push X on the stack. So this can be shown as A dollar X dollar A X X X. So it means that if an A occurs and if the stack top is either dollar or X, then we push X onto the stack to make the stack top as X dollar or XX. Now if we encounter a B, then we have to move to state Q1. Okay, so for this the stack top has to be X. If X is not there, then there is an imbalance of A's and B's. So the stack top has to be X. So if the stack top is X and if the input is B, then we pop the X. So it can be written as or represented as Bx epsilon. Bx epsilon. So if the input is B and the stack top is X, then pop. This can be from Q0 to Q1 or from Q1 to Q1 itself, because we keep on repeating this process until we are left with an empty stack for a valid string. So if we have an empty string, that is all the characters have been passed, then we move to state Q2, that is the string has been accepted. So we can write this as epsilon empty string comma dollar. Dollar is the bottom of the stack. So if we get a dollar, that means that the stack is empty. Then what we do is we move to Q2 and we keep the input as dollar and we accept the string because Q2 is in the final state. Now step 3 is specifying the remaining tuples. So the remaining tuples are Q, sigma, gamma, Q naught, Z naught and F. And for convenience, I've shown the state diagram that we designed earlier. So Q is the list of states. So the states we can see are Q0, Q1 and Q2. So Q is Q0, Q1 and Q2. Sigma is the set of input symbols. So the input symbols, as we can see, is either A or B. From the problem itself we can see that the input will be either A or B. So it is A or B. Gamma is the set of stack symbols. Stack symbols are the symbols present on the stack. We know that we push and pop X, so X has to be a stack symbol, and also the dollar sign, which signifies the bottom of the stack or the empty stack, that is also a stack symbol. So the stack symbols are dollar or X. Q0 is the start state. Start state is the one pointed by the arrow, so that is Q0. Z0 is the state which signifies the stack bottom or the empty stack, and that is dollar. F is the final state. Final state is the one with concentric circle, and that is Q2. Step 4 involves taking examples and solving them with our design machine to see if our logic is correct or not. So first let us take a correct string, which is AABB. This string is obviously correct because there are equal number of A's and B's, and all A's occur before all B's. So for this, to see how the machine computes, we make use of delta t function. Delta t function comprises of three things: the current state of the machine, the remaining string which is to be parsed, and the contents of the stack. So initially the state of the machine is Q0, the string which is to be parsed is AABB, and the content of the stack is dollar, that is empty stack. So now we have the state as Q0 and the input character as A and the stack top as dollar. From the diagram we can see that if the input is Q0 and the input character is A, and if the stack top is dollar, then we must push an X and keep the state as Q0. So the delta t function becomes Q0 ABB because the leftmost A has been parsed, and the stack becomes X dollar because an X has been pushed. Now we have the input character as A, the current state as Q0, and the stack top as X. So from the diagram we can see there is such a rule which states that we have to push another X on top of the stack so that the stack becomes XX. So we pushed an X on top of the stack, so the stack becomes XX dollar. The state remains the same Q0, and the input becomes BB because the A has already been parsed. So now the input is B and the current state is Q0 and this stack top is X. So we can see that there is a rule which states that if we have state Q0 input as B and stack top as X, then we must pop and move to state Q1. So the delta T becomes Q1, B, X dollar. The X, one X pops off, so the stack becomes X dollar. One B goes away because we've already passed that B, and the state changes from Q0 to Q1 according to our diagram. Now we are in state Q1, the current input is B and the stack top is dollar. So from the diagram we can see that there is such a rule which states that we must pop and we must stay in the same state. So it becomes Q1, epsilon, because removing B we are left with nothing, so that is epsilon, and the stack becomes dollar because the X pops off. Now we are in state Q1, the input is epsilon and the stack top is dollar. So according to our diagram, if such a case occurs, then we keep the dollar as dollar and we move to state Q2. So we move to state Q2, epsilon remains epsilon because there is nothing like removing epsilon. If we remove epsilon, then we are still left with epsilon, and according to our rule, dollar remains dollar and our state has only changed. So if we are in state Q2, that means that we are in our final state because Q2 is marked with two concentric circles. So if it is in final state, and if it has halted, then Q2 is final state and it is accepted. Now let us look at an incorrect string AAB. This is obviously incorrect because there are unequal number of A's and B's. So initially we are in state Q0 and the string is AAB and the stack is dollar. Now, so this means that one X has to be pushed. So the stack becomes X dollar. Now we are in state Q0 and the input is A and stack is X. So again we must push an X. So the stack becomes XX dollar and the string is B. Now with B and state Q0 and stack top as X, we must pop. So the stack becomes X dollar and the remaining string becomes epsilon and the state is Q1. Notice that there is no such rule which is for this combination of inputs, that is state Q1, the string epsilon and stack top as dollar. So we get stuck in this state Q1. Since Q1 does not belong to a list of final states, the string is rejected, as we might have predicted before. So we can see that this logic works for both correct and incorrect strings. So our logic is correct. Thank you for watching this video. I hope you found it useful. If you did, then please like, comment and subscribe for more. Thank you.